Business Calc 2, Section 8.2 on streams of income, including a review of present and future value under continuous interest. Recall that the function f of t is the flow rate as a function of time in years. So you think of a substance such as water flowing in at a variable rate f of t. So the water could be speeding up or slowing down as time goes on, or it could be constant. The simplest case is where f of t is k, a constant rate, so that's in dollars per year, over an interval of time, b years. And the total amount paid is bk dollars. That's the product of the rate, k, times the interval of time, b. So this is just the area of the rectangle over the interval of time from 0 to b. And that area is the integral from 0 to b of k dt, where remember k is that constant flow rate. This is nothing more than saying if you get paid $100 per year for, say, 10 years, then your total amount paid is $1,000. In general, the total income over b years with the flow rate f of t is the integral from 0 to b of f of t dt. Again, that is the area under the curve f of t from 0 to b. Here again, f of t, the function, is the flow rate expressed in dollars per year. Here you think of f of d dt as the amount you make over a thin interval of width dt, and then you take the integral, which is the limit of the sum of all these amounts, resulting in the total amount paid, which equals the area under this curve. So here's an example where the given flow rate is the function f of t equals 5,000 e to the 0.04 t. So the total income over 25 years is the integral from 0 to 25 of 5,000 e to the 0.04 t. So that function there is just the flow rate, which is given. That then is equal to 5,000 times 1 over 0.04. So the 1 over 0.04 is 25 e to the 0.04 t. You evaluate that and you get 125,000 times e to the 1 minus e to the 0, which is 1. And then it turns out to be about $0.2 million, or 215,000. Here's a brief present value reminder. Remember, if you have an amount f paid t years in the future, you have the equation f equals p e to the rt, or PERT. And p is the value at time 0, or the present value. Therefore, you have p is f e to the minus rt. Remember, the minus sign means you are inverting e to the rt. In other words, the present value, or p, is equal to f e to the minus rt. So there's the other version of the PERT formula here, solving for p in terms of the future value f. So don't confuse these two. E to the rt is a number bigger than 1, and e to the minus rt is the shrink factor, so that's a number less than 1. It's a fraction. P is the value now, and it is considered to be equivalent to the future amount, f, at time t. So using these formulas, we can go backwards and forwards in time and get equivalent values. And there's an underlying assumption of a continuous interest rate, r. That interest rate, r, is a standardized amount based on some published interest rate. So suppose you were promised $1 million in 100 years, assuming 1% interest. The present value is p equals 1 million times e to the minus 0.01, so that's the e to the minus r, and the t is 100 years. And you calculate that out to be $0.369 million, or $369,000. So that's how much your $1 million 100 years in the future is worth now. That is the present value. For comparison, suppose you are assuming 10% interest, then we get p is equal to about $45. So the interest rate matters a lot. To say the same thing, if assuming 10% interest, if you have $45.40 now, in 100 years at 10%, you will have $1 million. Now, returning to income streams, we have the flow rate f of t and interest rate r. Then the present value of the income stream is, given by the formula, p or pv is the integral from 0 to b of f of t times e to the minus rt dt. I should emphasize that rather than talking about a single payment in the future, this is a stream of payments that stretch out over the interval from 0 to b. And the idea is that over a small interval of length delta t in time, then the present value of the chunk of income is f of t times delta t. So the present value of that chunk of income is f of t times e to the minus rt delta t. Now, forming the Riemann sums and adding these amounts up and then taking the limit as delta t goes to 0 results in the present value integral as shown above. So that's the main integral in this section. Now, to get the future value at time b in the future, so there's that endpoint b, you just multiply the present value as computed before and multiply by e to the rb. So that's just the PERT formula applied to the present value of the stream at the time b in the future. To compare this with the Book's formula, you have the future value at time b in the future is equal to the present value times e to the rb, as I just said, and that is the integral from 0 to b of f of t e to the minus rt dt, all times e to the rb. So that e to the rp is a factor which you could write on the inside if you like, but there's no reason to do that, but that is how the book does it. So just for the sake of comparison, if you did write the e to the rb on the inside, there it is, then you'd collect the e to the r terms, you get e to the r times b minus t in the exponent, and that is the Book's formula. But I think it's better just to compute the present value first, do that integral, and then multiply by e to the rb in order to get the future value at time b. So here's the simple constant flow rate example. Suppose you have a flow rate of a constant $2,000 per year over b equals 10 years at 8%. Then the total amount paid is 2,000 times 10, or $20,000. And then, and that is also the integral of f of t from 0 to 10. And you see that is just, again, 20,000, which is 2,000 times 10. Okay, the present value of this stream of payment is e to the minus rt f of t dt, so that's 2,000 e to the minus 0.08 t dt. Okay, and you calculate the integral, and you integrate and you divide by 0.08, so that gives you minus 2,000 over 0.08 times e to the minus 0.08 t from 0 to 10. And now you plug in reverse order, absorb that minus sign, and you get 2,000 over 0.08 times e to the 0, which is 1, times minus e to the minus 0.08 times 10, which works out to be a little less than $14,000. The future value is gotten by multiplying that amount here by e to the rb, so that's e to the 0.08 times 10, and that gives you a little more than $30,000. So the future value is a lot more than the present value, as always. The total interest paid out at the end of 10 years is the future value minus the total amount paid. So the total amount is that $20,000 from above, and that difference is the interest, which is a little more than $10,000. So the total interest is the future value minus the total amount. So you have the three values: the total amount, $20,000, the present value, and then the largest amount, the future value, at the end of 10 years. Here's another example with a non-constant flow rate. Suppose the flow rate is 2,000 e to the 0.07 t dollars per year over a period of 10 years, again at 8% interest. The total amount paid is the integral of the flow rate, so you get the integral from 0 to 10 of f of t dt, which is then the integral from 0 to 10 of 2,000 e to the 0.07t dt. And you work that out to be 2,000 over 0.07 after you integrate times e to the 0.07t, and you just plug in 10 and 0. Notice that when you plug in 0, you get 1, and that works out to be almost $29,000. On the other hand, the present value of this stream of payment is the same integral, but you insert the e to the minus RT factor, that shrink factor. So there's the integral, 2,000 e to the minus 0.08t, there's 8% interest, times e to the 0.07t. Now you combine those two exponentials and you get 2,000 e to the, you subtract the exponents and you get minus 0.01t dt. And now you do the integral and you get minus 2,000 over 0.01 after anti-differentiating times e to the minus 0.01t from 0 to 10. Now I'm going to plug in reverse order and absorb the minus sign, and I get 2,000 over 0.01, or 200,000, times 1, that's e to the 0, minus e to the minus 0.01 times 10. And you calculate that out to be about $19,000. Notice that's a smaller amount than the total amount paid. The future value then is gotten by multiplying the present value times e to the 0.08 times b, or 10. So that's the e to the RB factor to give you the future value, and that is about $42,000. Okay, and now the total interest paid is the future value, just computed, minus the total amount paid, and that is a little more than $13,000. Of course, you might want to rewind this or pause it and make sure you see all the steps and all the details. As a final general example, suppose you have a constant flow rate Q. Okay, so that's a number. And you have little b years at continuous interest rate R. Let's derive the following formula for the present value of this stream of payment. So what we're shooting for is Q over R times 1 minus e to the minus RB. And here's a proof of that formula. The present value is the integral from 0 to b of e to the minus RT times the flow rate, which is Q dt. And we do this integral, and when you anti-differentiate, you get a minus R on the bottom there, and it's from 0 to b, so you plug in and we'll absorb that minus sign. And so we get Q over R times 1 minus e to the minus RB, and that's an amount in dollars. And that's the formula that we were shooting for. The final question here is, what happens to this if B is relatively large? So what happens to this amount when B is large? Well, the e to the minus RB factor here will tend to 0. That's because it's e to the RB really in the denominator. So that goes to 0. So the limiting value is simply Q over R. So this says that the present value of your stream of payment for large values of B is given by this really simple formula Q over R. The striking thing about this is that if you go far into the future, say decades into the future, then the limiting value does not depend on time. We'll return to this idea in the near future, but for now, that is the end of section 8.2 on streams of income.